I hope you are doing very well. So, welcome to JEE 45 days crash course. So, today we are going to start day 31. Okay, so I am Brijesh Kumar. So, let's begin with the class. So, today we are going to start day 31 of our JEE 45 days crash course. So, you can see today we will be covering GOC part 3. Okay, so you can see here general organic chemistry, and in this we will be discussing purification and characterization of organic compounds, basically like qualitative analysis, quantitative analysis, right? Okay, so you can see the syllabus as well, then you can see the approximate weightage, and you can see the topics to be covered today. So today's topics to be covered: first, purification techniques, some basic techniques like crystallization, distillation, sublimation, differential extraction, chromatography, right? Chromatography principles and their applications. Then we will be discussing qualitative analysis for the detection of carbon, hydrogen, nitrogen, sulfur, phosphorus, halogens. Then quantitative analysis of organic compounds, and at the last we will be discussing some important questions for JEE exams. So let's begin with the methods of purifications of organic compounds. So purification techniques, you can see crystallization. First of all, we will be discussing crystallization. The name is itself suggesting that crystal forming is there. Okay. So you can see crystallization. It is based on the differential solubility of a compound in a hot and cold solvent, right? What will be the process? You can see here. First, dissolve the impure compound in a hot solvent. Okay, where it is highly soluble. Okay, then filter the hot solution to remove any insoluble impurities. If any insoluble, like suppose this is the hot solution, and pour the impure substance here, right? First of all, this is the hot solution, then dissolve the impure compound into this hot solution. Then what happens? Then it becomes, it gets soluble, and then filter the hot solution if any insoluble impurity is present, right? To remove any insoluble impurities. Cool the solution slowly, allowing the pure compound to crystallize out, and then filter the cold solution to collect the crystals and wash them with the cold solvent to remove any type of remaining impurities, right? Then you will get crystals. You can see here the diagram. This is the solvent, this is the impure solid. You can use this glass rod to stir to dissolve this solid. Then you can see the solution is to be heated to evaporate most of the solvent, so that you will get crystal. This hot solution is allowed to cool to the, this hot solution, this is the hot solution, and this is allowed to cool to obtain the crystals, right? And you can see on a filter paper you can obtain these crystals, right? The cold solution is poured off, obtain the crystals by pressing them between sheets of filter paper. So what are the applications of crystallization process? It is used to obtain pure substances from impure mixtures, and such as like in the production of pharmaceuticals or chemicals. Okay, it is suitable for solids with high melting points and good solubility in hot solvents. Okay, because we are heating here. Okay, examples like benzoic acid, naphthalene, and urea. Next technique is distillation technique. Principle: it is used for the separation of liquids based on their different boiling points. Okay, what are the types? First type is simple distillation, second type is like fractional distillation, third is like vacuum distillation. Simple distillation is used for the separating liquids with a significant difference in boiling point, right? When there is a significant difference, okay, like 100 degrees Celsius, 40 degrees Celsius, 30 like 60 degrees Celsius, like the fractional distillation, when the separating liquids are having close boiling points, right? When the vapor is passed through a fractionating column for further separation. And vacuum distillation, definitely vacuum word is here, so it is used for liquids with high boiling points or those prone to decomposition at normal pressure. So you can see the diagram of distillation. This is for simple distillation. You can see this is the round bottom flask, and we are heating. You can see this is the thermometer to check the temperature, right? To sink, this is the hole, okay, and this is condenser. Then you will get, this is water inlet, and then you will get liquid substance here. So the vapors of a substance formed are condensed, right, through this with the help of this condenser, and the liquid is collected in this conical flask. Okay, in this case distillation under reduced pressure, you can see capillary to regulate the air. This is the capillary, this is the stopcock, again to sink, This is the manometer to measure the pressure as one. This is water inlet, and you can see this is the distilled liquid, and this is the vacuum pump. So a liquid boils at a temperature below its vapor pressure by reducing the pressure, right? By reducing the pressure, that is, these are two diagrams. Next, distillation applications. So it is widely used for the purification of liquids like such as in the production of alcoholic beverages or petroleum refining. Very interesting. Suitable for liquids with well defined boiling points and minimum decomposition at boiling temperature. Examples like ethanol water mixture, you can see alcoholic beverages, crude oil separation, purification of high boiling liquids, right? Next technique is sublimation. Sublimation, you have heard these simple techniques in your lower grades as well. So sublimation, definitely like camphor, solid iodine, dry ice, these are sublimable substances. So direct conversion of solid into vapor and back into solid without passing through the liquid state. What will be the process? Heat the impure solid in a sublimation apparatus. The pure compound sublimes and condenses on a cool surface as purified crystals, and any non-sublimable substance is present or impurity is present, you can it will remain in the bottom of the apparatus, right? And you can separate them. Applications, it is used to purify substances that sublime, like such as iodine or camphor, naphthalene, anthracene, by separating them from impurities that do not sublime. Okay, so one substance is sublimable, another is not sublimable. That is the point here. Suitable for solids with high vapor pressure and low decomposition temperature. Examples I told you already: iodine, camphor, naphthalene, dry ice, right? You can use these examples. Dry ice, etc. Next is extraction process. What is the principle? Selectively it dissolving a compound from mixture into a suitable solvent, followed by the separation of the layers and evaporation of the solvent. Types like liquid extraction and solid liquid extraction. Separating two immiscible liquids like oil and water, you can separate them with the help of this separating funnel. You can see where the desired compound dissolved preferentially in one layer. Solid liquid extraction, extracting a compound from a solid mixture using a suitable solvent. You can see this is the solvent layer, okay, before extraction, and this is the organic compound in aqueous layer, okay, organic compound in aqueous layer, and this is the aqueous layer then, and this is the organic compound in solvent layer, okay, this green color. So before extraction and after extraction, you can see the differential extraction. Extraction of compound takes place based on the difference in solubility, based on difference in solubility. I hope you are very much clear about this. Next, what are the applications? It is used to separate and purify organic compounds from mixtures, such as in the extraction of caffeine from tea leaves, right? It is suitable for separating compounds with different solubilities, different solvents, as well as examples like caffeines from coffee beans and essential oils from plant materials. Next technique is chromatography technique. What is the principle? Chromo means like color, okay. It is the principle is what? Separation of components in a mixture based on their different rates of movement through a stationary phase. One is stationary phase here, and due to varying degrees of interaction with the mobile phase. So there are two phases. One is stationary phase, another is mobile phase. Types, there are three types majorly, like we are discussing three types apart from this, like HPLC, right, gas chromatography, and other chromatographies are also there. So what is paper chromatography? It uses paper as the stationary phase and a liquid mobile phase, okay. Column chromatography used a packed column with a stationary phase and a liquid or gas mobile phase. And TLC, that means thin layer chromatography, uses a thin layer of stationary phase on a plate and a liquid mobile phase. You can see the diagram. In paper chromatography, you can see this is the baseline, okay. This is the spot that I marked on the paper, chromatographic paper. This is the jar and this one is the solvent. Then solvent rises, and what happens? You can see this is the cardboard, chromatographic paper, again jar, spot and baseline. So you can see spot travels some distance, right? Based on that we have to calculate the RF value. So paper chromatography paper in two different shapes, you can see here. Next one is column chromatography. You can see different columns are there. This is solvent, this is the mixture of compounds A, B and C. Then you can see adsorbent, that is the stationary phase, and this is the glass wool. So what happens? This is the mixture of A, B and C. Now you can see the mixture is getting separated, A and then B plus C. Now you can see A and B and C are separated out. So this is the method using the column chromatography, right? You can see the solvent is solvent, and this is the stationary phase, okay. Next one is TLC, thin layer chromatography. The thin layer chromatography and paper chromatography are similarly, like in paper chromatography we have to use chromatography paper. In thin layer TLC we have to use a what? You can see glass plate. Okay, adsorbent coated on glass plate. This is the sample dot, this is solvent, this is baseline, you can see this is the baseline, and this is jar. Solvent front, this is the front of solvent. Spot distance, you can see, you can measure the distance of solvent, and you can see the you can measure the distance of spot, right, distance traveled by spot. So this is the developed chromatogram. Next is the application and examples of chromatography. Applications, it is widely used in various types of fields such as like forensic analysis, pharmaceutical, quality control, or environmental monitoring. It is very interesting and important as well. It is suitable for separating complex like mixtures and purifying small amounts of compounds. Examples like separating pigments, right, identifying functional groups, analyzing reaction mixtures. So chromatography is a very useful method. Apart from this, you can see here the next topic is qualitative analysis for the detection of carbon, hydrogen, nitrogen, sulfur, phosphorus, and halogens. Carbon capital C is the symbol, hydrogen capital H, nitrogen is capital N, sulfur is S, phosphorus is capital P, and halogen we are representing with capital S. The next point is here materials and reagents. What are the materials and reagents that we have to use? Sample substance, first of all the organic compounds, right, and then test tubes, test tube rag, distilled water, and some chemicals like some reagents like nitric acid, sodium hydroxide solution, strong base, silver nitrate solution AgNO3, barium chloride solution BaCl2. Apart from this, lead acetate solution PbCH3CO whole twice, dilute HCl, right, hydrochloric acid, dilute sulfuric acid, H2SO4, potassium iodide solution, and starch solution you have to use. You can see first of all we are discussing the detection of carbon and hydrogen. What will be the procedure? Carbon and hydrogen can be detected in a compound by heating it with copper oxide. You can see copper oxide, right? This is copper oxide and Cu2 plus is here, right? So carbon is getting heated with copper oxide. You will get copper and CO2, right? So carbon present in the compound is oxidized to CO2, carbon dioxide, which can be tested by reacting it with lime water. You know very well when we are passing CO2 through lime water, you will get turbidity, right? Why? Due to the formation of CaCO3, which is calcium carbonate, right? So you can see the reaction between carbon dioxide and calcium hydroxide, that is lime water, aqueous calcium hydroxide, and it can be represented CO2 plus CaOH whole twice gives CaCO3, which is calcium carbonate, and you can see the precipitate form, white curdy precipitate formed here, plus H2O. This reaction result in the formation of turbid solution, which is due to the formation of CaCO3, calcium carbonate, and you can see the reaction between carbon and copper oxide, that is C plus carbon plus 2CuO gives 2Cu plus CO2 gas. Similarly, detection of hydrogen, you can see hydrogen present in the compound is oxidized to water. You can see hydrogen reaction with copper oxide, 2H plus CuO, copper oxide gives Cu, copper plus water, right? You can see which can be tested by reacting it with anhydrous copper sulfate. Then this water that is produced in this reaction is treated with copper sulfate. You will get copper sulfate pentahydrate, which is also named as blue vitriol, and this is blue in color. This is blue in color. The reaction between hydrogen and copper oxide can be represented by the equation. You can see 2H plus CuO gives Cu plus 2H2O. Cu plus H2O, not 2H2O, okay. And you can see the reaction between water and copper sulfate also. Water and copper sulfate will provide copper sulfate pentahydrate. And you can see CuSO4 plus 5H2O gives CuSO4.5H2O, which is copper sulfate pentahydrate. Penta we have to use for this 5. And this is water of crystallization. And this is also named as blue vitriol because this is blue in color. I am writing blue vitriol also, right? Copper sulfate pentahydrate also named as blue vitriol. Blue vitriol, okay, this is important, blue vitriol. Next one is here, detection of nitrogen. Sodium fusion extract is boiled with iron sulfate. Iron sulfate is nothing, that is FeSO4, okay. If you want to detect nitrogen, so you can use these steps. The mixture is then acidified with concentrated H2SO4, which is sulfuric acid. Very interesting. The presence of nitrogen is confirmed by the formation of Prussian blue color. Okay, the first point, sodium fusion extract we have, right, and that is boiled with iron sulfate FeSO4. Then the mixture is acidified with the help of concentrated H2SO4 strong acid. Then the presence of nitrogen is confirmed by the formation of blue color. Sodium cyanide react with iron sulfate FeSO4 to form sodium hexacyanide. Sodium hexacyanide. Heating the mixture with concentrated H2SO4 oxidizes some iron Fe2 positive ions to Fe3 positive ions, right? The Fe3 positive ion react with sodium hexacyanide, which is a coordination compound, right, to produce iron 3 hexacyanide, right, and in 2 plus state, okay, or ferrocyanide, you can say, which is Prussian blue in color. So you can see the reaction 6Cn negative plus this is cyanide ion 6Cn negative plus Fe2 positive gives FeCN6 FeCN whole 6 4 negative. Okay, you can see then 3 FeCN whole 6 4 negative reacts with Fe3 positive, you will get Fe4 FeCN whole 6 whole thrice dot XH2, and this is Prussian blue, which is blue in color, right? This is Prussian blue, which is blue in color, this compound. Let's move to the next detection of sulfur. So sodium fusion extract is acidified with acetic acid for the detection of sulfur. Then lead acetate is added to the acidified extract, that is the point. A black precipitate of lead sulfide, which is PBS, forms. The formation of black precipitate indicates the presence of sulfur. So you can see the reaction S2 negative reacts with Pb2 positive gives PBS lead sulfide, which is black in color. This is black precipitate of this lead sulfide will form. Next point is here, that is interesting. Sodium fusion extract refers to a solution obtained by fusing the sample with sodium metal, okay, followed by dissolving it in water. That is the point. Sodium nitroprusside, what is sodium nitroprusside? Is used as a reagent to detect the presence of sulfur. So you can see this is the one method, this is the another method. So you can see this is the second method. Sodium fusion extract refers to a solution. What is that? That is obtained by fusing the sample with sodium metal, right? We have to take sodium metal in small capillary tubes, then heat it like this, okay? You know, Lessingen test, right? Sodium nitroprusside is used as a reagent to detect the presence of what? Sulfur. When sodium fusion extract is treated with sodium nitroprusside, right, the appearance of violet color indicates the presence of sulfur. The reaction between sodium nitroprusside, this is sodium nitroprusside, and this is sulfur, right? Sulfide ion actually, right? This is sulfur, or you can say sulfide ion. Sulfur results in the formation of complex compounds that exhibit a violet color. This compound exhibit a violet color, right? This color change is a reliable and commonly used test to confirm the presence of sulfur in a sample. So this is a reliable test, okay? Again, I am repeating the step. First of all, you have to take sodium fusion extract, right? That means a solution that is obtained by fusing the sample with sodium metal, right, followed by dissolving it in water. Then sodium nitroprusside is used as a reagent to detect the presence of sulfur, right? You have to make sodium fusion extract, you know sodium fusion extract, how you can make sodium fusion extract, right? You have to mix the compound, right? The compound that you have, okay. When sodium fusion extract is treated with sodium nitroprusside, the appearance of a violet color indicates the presence of sulfur. So due to the formation of this compound, due to the appearance of violet color, the sulfur presence is confirmed, right? And this is definitely a reliable change, right? Okay, let's move to the next. That is what? Detection of phosphorus. Compound is heated with an oxidizing agent, sodium peroxide, okay, Na2O2. Phosphorus present in the compound is oxidized to phosphate. Phosphate is what? PO4 3 negative, phosphate ion. Solution is boiled with nitric acid, which is HNO3. Solution is treated with ammonium molybdate, and a yellow coloration of precipitate indicates the presence of phosphorus. So let's see the reaction. You can see Na3PO4, this is phosphate ion, PO4 3 negative, reacts with nitric acid, you will get S3PO4 and NaNO3, right? You can see here, you will get this compound. Then this S3PO4 reacts with ammonium molybdate. You can see ammonium molybdate, okay. That means 12 NH4 whole twice MO molybdenum O4 plus 21 HNO3, you will get NH3 whole thrice PO4, that means ammonium phosphate, dot 12 MOO3, that means molybdenum, this is molybdenum, okay, plus 21 NH4 NO3 plus 12H2. So this will be the reaction. So you can see yellow coloration or precipitate indicates the presence of, so yellow color is comes due to the formation of these precipitate, okay. That is the point here. This is the detection of phosphorus. Let's move to the next one. So detection of phosphorus is done, and the next one is detection of halogens. Sodium fusion extract, you can make sodium fusion extract, you know very well, and then it is acidified with nitric acid, which is HNO3. The acidified solution is then treated with silver nitrate. Silver nitrate is AgNO3. A white PPT, here white PPT, so you have to remember the color because the question can ask directly from colors, okay, and the compounds or the reactions, okay. White PPT soluble, what I can say, white PPT soluble in ammonium hydroxide, which is a weak base. NH4OH indicates the presence of chlorine. NH4OH indicates the presence of chlorine. A yellowish precipitate springly soluble in ammonium hydroxide indicates the presence of bromine. If white PPT is formed and which is soluble in good soluble in ammonium hydroxide indicates the presence of chlorine, okay. The third point indicates the presence of chlorine. And a yellow PPT is formed which is springly soluble in ammonium hydroxide indicates the presence of bromine, right? So fluorine, chlorine, bromine, iodine, na? You can say a yellow PPT insoluble in ammonium hydroxide indicates the presence of iodine, right, which is insoluble. If a yellow PPT is formed which is springly soluble in ammonium hydroxide, that present gives the presence of what? That indicates the presence of bromine. But if a yellow precipitate is formed which is insoluble in ammonium hydroxide is a weak base, you know very well, that is NH4OH, indicates the presence of iodine, If nitrogen or sulfur is also present along with halogens, right, you can see the sodium fusion extract is boiled with concentrated nitric acid first. This step is done to decompose any type of cyanide or sulfide of sodium formed during Lasigian test. Cyanide or sulfide, cyanide ion Cn negative or sulfide ion S2 negative can interfere with the silver nitrate test of halogens, AgNO3 test of halogens, because when AgNO3 is reacting, you will get like AgCl, you will get like AgBr, you will get like AgI, etc. You can see the next part is quantitative analysis of organic compounds. So in quantitative analysis, so we have done with this detection of halogens part. So in quantitative analysis, we will be discussing the estimation of elemental content in a formation, right? So you can see here the sample preparation. First of all, take a representative sample from the given formation. Ensure the sample is finely ground and homogeneous, okay? It should be finely ground. So you can see, first of all, we will be discussing the carbon estimation. So an organic compound is burnt in the presence of excess oxygen and copper oxide. First of all, you can see the carbon in the compound is oxidized to carbon dioxide. We have seen the reaction, right? C plus CuO gives Cu plus CO2, like this, okay. The hydrogen in the compound is oxidized to form water. We have seen the reaction of hydrogen with CuO as well. The mass of carbon dioxide and water produced is measured. Then you can measure the mass of carbon dioxide and water. Then from the mass of carbon dioxide produced, the amount of carbon in the compound can be calculated, right? Because you can know very well, in CO2 we have, if 1 mole of CO2 we have, and if I am taking the mass in gram per mole, so we have 12 gram per mole carbon and 32 gram per mole oxygen, total oxygen, right? So total 44 gram per mole is the molar mass of what? CO2, right? Like this. So from the mass of water produced, the amount of hydrogen in the compound can be calculated. That means if you have organic compound, right, and which contains hydrogen and carbon, so you can react them with copper oxide. You will get two things. One is carbon dioxide, another is water, right? So carbon dioxide, from carbon dioxide you can calculate the mass of carbon, and from the H2O you can calculate the mass of hydrogen, right? You can see the general reaction. If any compound contains X carbon and Y hydrogen, so CXHY, it will react with X plus Y by 4. You will get X CO2 plus Y by 2 H2O, Y by 2 H2O, X plus Y by 4, okay. So you can see here, let the mass of organic compound be m gram. Mass of water and carbon dioxide produced be m1 and m2 gram, right? Suppose mass of water is m1 gram and mass of carbon dioxide produced during the reaction is m2 gram. So you can use this formula directly. Percentage of carbon is 12 into m2. m2 is the mass of carbon dioxide into 100 divided by 44 is the total mass of carbon dioxide into m. That is the mass of organic compounds, and you will get the answer in percentage. This is the percentage of carbon. You can see the estimation of carbon and hydrogen diagram. You can see this is the pure dry oxygen. You can see this is the combustion tube, and you can see this is the burner. Sample in platinum boat, okay. This is the platinum boat, and in this platinum boat, inside this platinum boat we have sample. These are CuO pellets, copper oxide pellets. This is anhydrous CaCl2, calcium chloride. This is KOH solution and this is excess of oxygen. So estimation of carbon and hydrogen, water and carbon dioxide formed on oxidation of substance are absorbed in anhydrous calcium chloride. You can see the bubbles na, and potassium hydroxide solution respectively contained in U tubes. Okay, in this tube anhydrous, in the first U tube you can see anhydrous CaCl2, in the second U tube what KOS solution is present, right? Okay, so you can see CuO pellets, copper oxide pellets are also there. I hope you are very much clear. So CXHY reacting with X plus Y by 4 CuO, okay, gives X CO2 plus Y by 2 H2O. You can see total H2O is total oxygen. If you want to check the balancing, so Y by 2 and plus 2X. Y by 2 plus 2X total oxygen is here, right? And if you want to check oxygen here, so total oxygen is X plus Y by 4 and X plus Y by 4. X plus, I am writing here, it is X plus, let's write here, so Y by 2 plus 2X, and in the left side X plus Y by 4 oxygen. So if you will divide this equation left one with 2, so you can see you will get Y by 4 plus X. So X plus Y by 4, same na? So that is the point here, okay? So this is the balanced chemical equation. So X plus CXHY plus X plus Y by 4 CuO gives X CO2 plus Y by 2 H2O. You can see the formula. Then you can see the formula. Then you can see the nitrogen estimation. Nitrogen, in nitrogen estimation, we have to conduct a nitrogen analysis using the Gildan method or Dumas method. So there are two methods. We will be discussing these two methods one by one. Calculate the percentage of nitrogen based on the weight of nitrogen compounds produced during analysis. First of all, you can see if any compounds contain carbon, hydrogen and nitrogen is reacting with 2X plus Y by 2 CuO, you will get X CO2, Y by 2 H2O plus Z by 2 N2 plus 2X plus Y by 2 Cu. So you have to what? In the in this reaction Cu also formed, okay? In this reaction Cu also formed, okay? You can balance that part. So what I want to say, we are just detecting the carbon nitrogen estimation, right? So you can see here, now we are discussing the nitrogen estimation. So you can see the reaction CX HY and Z, okay? This is and that means X carbon, Y hydrogen and Z nitrogen is present, reacting with 2X plus Y by 2 copper oxide CuO gives X CO2, Y by 2 H2O, Z by 2 N2 plus 2X plus Y by 2 Cu. Okay, you have to learn this general reaction. Then you can see the nitrogen estimation. Suppose the mass of organic compound is m gram. Okay, volume of nitrogen collected is V1 ml, let's suppose. Room temperature is T1 Kelvin. Volume of nitrogen at STV P1 by V1 into 273 divided by 760 into T1, right? Volume of nitrogen at STP, that is standard temperature and pressure. This is the standard pressure, this is the standard temperature. You know very well P1 V1 is equal to P2 V2. So this is like V2, okay? This is like V2. P1 V1 by T1 is equal to P2 V2 by T2. P1 V1 by T1 is equal to P2 V2 by T2. If you want to calculate V2, what you have to do? You can do P1 V1 T2 by T1 into what? P2, right? T2 comes here and P2 comes here. Okay, like this. So P1 V1, this is T2, which is 273 Kelvin, and P2 is 760 and T1 is here, like this. Okay, let it be VML, where suppose the volume of nitrogen at STV be VML, right, capital V, where P1 and V1 are the pressure and volume of nitrogen. P1 is different from the atmospheric pressure at which nitrogen gas is collected. That is different. The value of P1 is obtained by the relation, right? The value of P1 is obtained by the relation P1 is equal to, because in atmosphere moisture is available, so we have to subtract the aqueous tension, right? So you can see P1 is equal to atmospheric pressure minus aqueous tension, then you will get the pressure of what? Pressure at which nitrogen gas is collected. Then you can see, we know very well generally 20,400 ml or 22.4 liter of N2 of any gas at STP contains 1 mole. that means contains, because N2 has 28 gram per mole, that means it contains 28 gram N2, right? 28 gram N2. So VML N2, if then 1 ml N2 contains 28 by 22,400 and VML contains 28 by 22,400 into V gram. So you can calculate the percentage of nitrogen. That means how can you calculate? What will be the 22 into V divided by 22,400 into my M, that is the total mass. That is the total mass. Okay. So given that is the that we are calculating, for which we are calculating, and divided by total, multiply with 100. Organic compound, when reacting with H2SO4, you will get ammonium sulfate, which is treated with a base, that is 2NaOH. You will get sodium sulfate, Na2SO4 plus ammonia gas, 2NS3 plus 2H2. Then this ammonia gas is again treated with H2SO4, you will get ammonium sulfate. I hope you are very much clear about the nitrogen estimation. So basically you have to learn this formula, which is very important. Right, you have to learn this formula. Okay, so you can see this formula is having 22 into V divided by 22 by 22,400 into M. So 22,400 is a constant number, 28 is a constant number, V is what? You know very well, V is the volume of nitrogen at STP, right? You can calculate using this formula, P1 V1 into 273 divided by 760 into T1, right? Into T1. I hope this is clear. And divided by M, and M is what? Small m. You can see here all the values. So M is the mass of organic compound. Okay, you can see the Dumas method. Okay, Dumas method and Jildar method, two methods are there. You can see CO2 is getting entered from here. You can see this is the copper oxide gauze, this one, this wired gauze. Okay, you can see this wired gauze. You can see then this is the CO plus organic compound, that means copper oxide plus organic compound. Okay, this one. Then you can see coarse CO, and then you can see this is the reduced copper gauze. This is the reduced copper gauze, and this is the furnace. These all things are under furnace. Okay, you can see there is a tube and there is a mercury seal, and this is nitrogen collected here. Okay, and this is the nitrometer which can measure the nitrogen. So Dumas method, the nitrogen compound yields nitrogen gas on heating it with copper oxide, that means CuO, in the presence of CO2 gas. Okay, the mixture of gases is collected over potassium hydroxide solution. Okay, this is potassium hydroxide solution in which CO2 is absorbed and volume of nitrogen gas is determined. Okay, with the help of this nitrometer. Let's move to the next part. This is the next calculation. Let's suppose the mass of organic compound taken is m gram. Volume of H2SO4 of molarity capital M taken is VML. So volume of H2SO4 we are taking VML. Volume of NaOH of molarity M used for the titration of excess of H2SO4 is V1 ml. So V1 ml of NaOH of molarity M, we are using molarity M, is equal to V1 by 2, because you know very well H2SO4 having N factor value is 2, right? N factor value is 2. V1 by 2 ml of H2SO4 of molarity M. Okay, volume of H2SO4 of molarity M unused, V minus V1 by 2 ml. Then V minus V1 by 2 ml of H2SO4 of molarity M is equal to 2 into V minus V1 by 2 ml of NH3 solution of molarity M. This is the simple calculation. Then 1000 ml of 1 molar NH3 solution contains 70 gram NH3. Definitely. So 14 gram of N N to 14 gram of N, that means nitrogen, to V minus V1 by 2 ml of NH3 solution of molarity M contains, M is what? Molarity. 14 into M into 2 into V minus V1 by 2 divided by 1000 gram, right? This is the point. So how can you calculate percentage? 14 into M into 2 into V. V is the volume of H2SO4 of molarity M taken, capital V, minus V1 by 2. V1 is the volume of NaOH of molarity M is used. Divide by 2 and divide by 1000. This is this. Multiply with 100 and divide by M. Okay, divide by M. So you can simplify this formula and you will get this 1.4 into M into, so the formula that you have to learn, 1.4 into molarity capital M into 2. V is the volume, V minus V1, V minus V1 by 2, V minus V1 by 2 upon small m. Okay, small is the mass of organic compound. This is the final formula that we have to learn to get the answer of the question. To get the answer of the question, this formula is important. Okay, again I am writing the formula: 1.4 into molarity into 2 V volume of H2SO4 minus V1 by 2. V1 is the volume of NaOH divided by small m, and for percentage everything is done in this formula, right? In this formula everything is done. This is the final formula that we have to learn for the estimation. Okay, so 1.4 into m into 2 into v minus v1 by 2 upon m. Again I am repeating these formula because we will be discussing some question. The point is here, note is here, Jeldan method is not applicable to the compounds. This is important. This is important. From here many times question can be asked, right? And you can see containing nitrogen in nitro. If nitrogen is present in NO2 form, azo groups if in N double bond N forms, and nitrogen present in the ring, for example pyridine. Okay, as nitrogen of these compound does not change to ammonium sulfate under these conditions. So if nitrogen does not change to ammonium sulfate under these conditions, so Jeldan method is not applicable to these compounds. So you have to remember, if nitrogen is present in nitro form, in pyridine form, like in nitrogen is present in ring, and if like this, if nitrogen is present like this, this is nitrogen like this, so nitrogen is present inside the ring, right? Nitrogen is a ring member, so definitely what happens, we cannot use the Jeldan method, okay, or azo group and azo group. I hope you are clear. You can see the Jeldan method systematic diagram. You can see in Jeldan method nitrogen containing compound is treated with concentrated H2SO4. You can see organic compound plus concentrated H2SO4 plus copper sulfate. This is named as Jeldan flask. Okay, this is named as digestion, that means heating in Jeldan flask. Okay, with the help of this burner, we are heating this mixture with the help of this burner. Okay, then what happens, to get ammonium sulfate, so from here we will get ammonium sulfate which liberates ammonia on treating with NaOH. So contents of Jeldan flask after digestion here, and with the treatment with NaOH, with the treatment of NaOH, that is sodium hydroxide, right? This is the Jeldan trap. Okay, and this is the water outlet, you can see here, water inlet you can see here, and this is the non-volume of the standard acid. So on treating with NaOH, ammonia is absorbed is non-volume of standard acid, right? I hope you are getting clear idea about this. This is the Jeldan method. Next, halogen estimations. First of all, perform a halogen analysis using techniques like the Mohr method or Volhard method. Then calculate the percentage of halogens such as chlorine, bromine or iodine based on the weight of halide ions produced during the titration process. Okay, so you can see a method or you can see a formula here. Let the mass of organic compound taken is m gram. Okay, m gram. Mass of AgX, silver halide formed, m1 gram. 1 mole of AgX contain 1 mole of X. You can see 1 mole of AgX, if you will break, you will get Ag positive plus X negative. That means 1 mole of X contains 1 mole of Ag and 1 mole of X negative, right? Mass of halogen in N1 gram of AgX. Atomic mass of X divided by molecular mass of AgX into m1 gram, right? Into m1 gram. Percentage of halogen, atomic mass of X into m1 gram divided by molecular mass of AgX, multiply with 100. Multiply with 100, you can calculate with the help of this. Okay, multiply with 100. I hope you are getting a clear idea about this formula. Okay, so this is the percentage of halogen. You can see we can use the Carius method here. This is the sealed capillary and approximately a length is 50 centimeter. 2 centimeter, and fuming HNO3 is here, AgNO3 is here, and organic compound. This black color you can see, this is the organic compound. So Carius method, halogen containing organic compound is heated with fuming nitric acid in the presence of silver nitrate, right? In the presence of silver nitrate. So you can use these formulas. Percentage of halogen, how can you calculate? Atomic mass of X, which is halogen, multiply with m1 gram which is the mass of AgX, silver halide formed, divided by molecular mass of silver halide. So from here you will get the number of moles exactly, right, given mass by molar mass, and multiply with 104 percentage. Okay, let's move to the next part, sulfur estimation. It use the combustion method, or you can see ESCHKA method, okay, SKA method, to estimate the sulfur content. Calculate the percentage of sulfur based on the weight of sulfur dioxide. So here sulfur dioxide produced during analysis. Suppose the mass of compound taken is m gram. Okay, the mass of compound taken is m gram. Mass of barium sulfate formed, BaSO4, is m1 gram. 1 mole of BaSO4 means 233 gram. BaSO4 contains 32 gram of sulfur, because you can see in BaSO4 only one sulfur is here. If only one sulfur, definitely it contains 32 gram of sulfur. That means 233 gram of BaSO4 contains 32 gram sulfur, right? So m1 gram BaSO4 contains, if 233 BaSO4, if I am writing, if 233 gram BaSO4 contains only 32 gram of sulfur, only 32 gram of sulfur, so 1 gram BaSO4 contains 32 divided by 233 gram of sulfur. So m1 gram of BaSO4 contains 32 divided by 233, multiply with not BaSO4, multiply with m1 gram of BaSO4. So you will get 32 divided by 233 into m1 gram of sulfur, m1 gram of sulfur. This is the point here. I hope you are getting a clear idea. So you can see 32 divided by 233 into m1 gram of sulfur. Then how can you calculate the percentage? So this is the amount that you want to calculate. That means this is the amount of sulfur divided by total, right? So 32 into m1 divided by 233 into m is what? M is the total mass, right? You can see of organic compound taken, multiply with 104 percentage. This is the estimation of sulfur. Now let's discuss the estimation of phosphorus. Phosphorus is P. First of all, conduct a phosphorus analysis using techniques like colorimetric method or the gravimetric method. Then calculate the percentage of phosphorus based on the weight of phosphorus compounds produced during analysis. So what type of phosphorus compounds produced? You can see here. Let's suppose the mass of organic compound taken is m gram. Mass of ammonium phosphomolybdate, okay, molybdate is m1 gram. So mass of organic compound is m gram. Mass of ammonium phosphomolybdate is m1 gram. Molar mass of NH4 whole thrice PO4, ammonium phosphate, okay, NH4 whole thrice PO4 dot 12 MOO3 is 1877 gram. Percentage of phosphorus, how can you calculate? You can see 31 into m1 divided by 1877, that is total, into 104 percentage divided by m. So you can use directly this formula, 31 into m1, which is the mass of m1 is the mass of ammonium phosphomolybdate, given mass. So given mass by molar mass, right? And 31 is what? Only one phosphorus is present here, only one phosphorus, okay, and multiply with 100 and divide by small m, which is the total mass. If phosphorus is estimated as Mg2P2O7, so percentage of phosphorus, how can you calculate? 62 into, because 2 phosphorus is here, for 1 phosphorus 31 gram, and for 2 phosphorus you can use 62 gram, right? 62 gram per mole also you can say. So 62 into m1 divided by total mass, molar mass of this Mg2P2O7 is 222 gram per mole, 222 gram per mole, right? So 62 divided by 222 into m1 into 104 percentage, where 220 or you can say 222 gram per mole is the molar mass of Mg2P2O7. M is the mass of organic compound taken. M1 is the mass of Mg2P2O7 formed, right? That will be given in the question. And 62, the mass of 2 phosphorus atoms present in the compound Mg2P2O7. I hope you are getting a clear idea about the phosphorus estimation formula. So the first formula is this percentage of phosphorus, and the second formula is this one. Okay, let's discuss some important questions for JEE exams. Important questions. So first question will be, the most suitable method for separation of 1:1 mixture of ortho and para nitrophenol is sublimation, chromatography, crystallization, and steam distillation. So orthonitrophenol is nothing, that is, this is orthonitrophenol, OH, and paranitrophenol is benzene, NO2, and OH. This is orthonitrophenol, and this is paranitrophenol. So we have orthonitrophenol and paranitrophenol. In this case, in orthonitrophenol, intramolecular hydrogen bonding takes place. Intra. But in case of paranitrophenol, intermolecular hydrogen bonding takes place. Now the point arises, what will be the effect of this intramolecular or intermolecular? Due to this intramolecular hydrogen bonding, this particular compound becomes stable, but it is not attached with the other compounds with a great interaction. That's why orthonitrophenol is steam volatile, but paranitrophenol is not, because paranitrophenol in itself is not stabilized, but it is stabilized by the intermolecular hydrogen bonding, and it will get attached with a greater interaction with other compounds, right? Suppose this is A, so inside A the bonding is strong, but A, between A and A the bonding is not very much strong, the interaction is not very much strong. Suppose this is B, so inside B the bonding is not very much strong, but between B and B the bonding is strong due to the intermolecular hydrogen bonding. That is the point here. Okay, the interaction is strong. Okay, let's move to the answer. So orthonitrophenol exists as a monomer because of chelation. You can see when rings are formed, when rings are formed, so that is known as chelate effect, and these structures are known as chelate, and this phenomena is known as chelation, and hence steam volatile. I told you already, due to the intramolecular hydrogen bonding, this compound becomes stable. This is stable. Okay, this is stable. Thus steam volatile, because this is stable in itself. The second compound will become stable in itself, but between these two compounds there will be no interaction, but between these two compounds the interactions are weak. Between these two compounds the interaction are weak. That's why this is steam volatile. Thus steam distillation method is used for the separation of 1:1 mixture, because in case of paranitrophenol there is what type of bonding? There is, you can see here, intermolecular hydrogen bonding, right? So this interaction is strong as compared to the this one. Okay, we are comparing these two. I hope you are getting clear idea. So what is the correct answer? Steam distillation. Let's move to the second question. Two solids we have, A and B, have appreciably different solubilities. The solubilities are different in water, but their melting points are very close. I told you already, if solubilities are different and melting points are close, the mixture of A and B can be separated by sublimation, fractional crystallization, distillation, or both B and C we can use. That's a very simple question. Fractional crystallization is used to separate two solids A and B having appreciable different solubilities in water, but their melting points are very close. So we have to use fractional crystallization. Okay, we can use fractional crystallization. Okay, so apart from melting point, we can use a proper word, that should be boiling point. Okay, their boiling points are very close, because their boiling point, melting point. Okay, in this case, in fractional crystallization we can use melting point, but in fractional distillation we have to use boiling point word. Okay, so don't get confused between fractional crystallization and fractional distillation. Okay, in fractional distillation boiling point are very close. So let's move to the next point. The next point is very interesting. That will be the third question. The distillation technique used for, just give me 1 second. Okay, boiling is for fractional distillation. The distillation technique used most suited for separating glycerol from spent lye in the soap industry. Okay, from the spent lye in the soap industry is fractional distillation, steam distillation, distillation under reduced pressure, or simple distillation. So four types of distillations are there. The point is here separating glycerol. So you can see here glycerol with high boiling point, which is approximately 290 degrees Celsius, can be separated from spent lye by distillation under reduced pressure. This process is used to purify liquids. So distillation under reduced pressure process is used to purify those liquids having very high boiling point. By this process, liquid is made to boil at lower temperature than its boiling point by lowering the pressure on its surface. That's very interesting process. Okay, so this is the distillation under reduced pressure. Okay, so what is the right answer? Option C. Let's discuss the next question. The addition of HCl to an alkene proceeds in two steps. Okay. The first step is the attack of H positive ion to what? H positive ion to the portion which can be shown as. So you can see here, this is the double bond electron density. This is the double bond, that means electron density and pi bond, right? So what will be the step? You know very well, whatever species is attacking, right? But always we have to show arrow from negative to positive, negative to positive. So this is showing positive to negative arrow and this bond is coming here. I think that's not correct. This is showing positive to negative arrow, that's not correct. So only the correct answer is B. So let's see the solution. The first step in the addition of HCl to an alkene proceeds as follows. You can see here, this is the alkene. Okay, suppose what happens, this is H positive, so it will attack on this H positive and it will attach this H positive like this. Suppose the H positive will attach to this carbon, so this carbon will get positive charge like this. So to understand this process, we can imagine like this: C double bond C, this is like a cleavage and negative charge comes here, that means bond breaking like this, and positive comes here, then H positive become negative positive. Okay, this is only for understanding part. Okay, not exact mechanism. Okay, this is only for understanding. Okay, so it will attack on this and it will get attached. Okay, it will get attached like this, like this. Okay, but always we cannot show like this. Okay, we cannot show like this. Always we have to show like the arrow from double bond to electrophile. Okay, double bond to electrophile, like double bond to H positive. Okay, always. Okay, never show like this. Okay, I hope this is clear. So you can see the first step. So what is the answer? So you can see, first of all, the breaking of like HCl. So you can see Cl will get negative charge, H will get positive charge, and then double bond will attack on this H positive, and you will get this bond becomes single, and hydrogen will get attached here. Okay, hydrogen will get attached here. So this is the first step in addition of HCl to an alkene proceeds. Okay, I hope this is clear. So you can see here the first step is only this one. Next is the lesion extract is boiled with dilute HNO3 before testing for halogens because why? What will be the reason behind this? Ag2S, silver sulfide, is insoluble in HNO3. AgCN is soluble in HNO3. Na2S and NaCN are decomposed by HNO3, and silver halides are soluble in HNO3. So you can see the solution. In order to decompose unreacted sulfide and cyanide, HNO3 is added. If any unreacted sulfide or cyanide is present, right, to decompose them, HNO3 is added. To decompose them, HNO3 is added. I hope you are getting a clear idea. Again, I am repeating, to decompose the unreacted sulfide which contains like S2 negative ions, that means like Ag2S, silver sulfide, and sodium sulfide, Na2S. And cyanide which contains Cn negative ions like NaCN, sodium cyanide, like AgCN, silver cyanide. HNO3 is added because you know very well HNO3 is a strong oxidizing agent, and HNO3 we are using here dilute HNO3. Okay, the next question is this. So you have to do this question as a homework. Okay, so match the following and choose the correct option: Dumas method, Geldal method, Carius method, and chromatography. You can see here, you know the concepts, right? We have covered the concepts. Now you have to only match the following from column 1 to column 2 and then choose your answer from their code, these given options A, B, C, and D. Next question you have to practice as a homework. For the estimation of nitrogen, 1.4 gram of an organic compound was digested by Zildan method. Okay, That means given mass of organic compound is 1.4 gram. And the evolved ammonia was absorbed in 60 ml of m by 10. Molarity is given here, m by 10. That means you can take 0.1 molarity. Sulfuric acid. Molarity of sulfuric acid is given. The unreacted acid required 20 ml of m by 10 sodium hydroxide. That means both molarities are same. Okay, for complete neutralization, the percentage of nitrogen in the compound is percentage of nitrogen. Simply you have to calculate. You can use the formula that I have given to you of percentage to calculate the percentage of nitrogen, right, according to Jaldan method as well. So you can use that formula and you will get the answer 6, 10, 3 or 5. Let's move to the next question. Which of the following statement is wrong? So statement is saying that using Lasigan test, nitrogen or sulfur present in an organic compounds can be tested. The statement is saying that statement B, using Bellstein test, the presence of halogen in a compound can be tested. Lasigan test fails to identify nitrogen in diazo compounds. In the estimation of carbon, an organic compound is heated with CuO in a combustion tube. So you know the concepts. We have covered so many statements today. So you can recall the concepts and you can practice this question. The next question is, in Jaldan method, the gas evolved from 1.325 gram sample of fertilizer is passed. So this is the given mass, right? Passed into 50 ml of 0.2030 normal H2SO4. 0.2030 normal H2SO4. 25.32 ml of 0.1980 normal NaOH are required for the titration. Okay, so normality is given right now, and you know very well molarity and normality relation, right? Normality is equal to n factor into molarity. Okay, so if you want to calculate the molarity, you can easily calculate, or even you can change the formula by using this relation, right? Normality divided by n, you will get molarity. So 50 ml volume is given of 0.2030 normal H2SO4, normality is given. 25 is required. You can see here 25.32 ml of 0.1980 normality is given of NaOH are required for the titration of unused acids. What will be the percentage of nitrogen in a fertilizer? So percentage of nitrogen you have to calculate. You can use even in this question, this is given Jaldan method you have to use. So go to that particular formula, use that formula. Everything is given here. You can if you want to calculate molarity, you can use this relation. Normality is equal to n factor into molarity. And the last question of this today's class, that will be this is the structure and we are using H positive and heat. What will be the answer? What will be the product? Consider the above written equation and reaction, and the product will be what? You have to tell me the product. Okay, so that's a very simple and easy question, and this is all about this today's class. So today we have discovered we have discussed what the qualitative analysis, some purification techniques, and quantitative analysis, right? That was very interesting topics. So thank you so much.